Hi everyone, so today I'm going to be solving the week 5, or are we week 6? Week 6 chemistry quiz. So we're going to start. It's really easy, no solving this week. You don't need a calculator for anything. Okay, so which of the following factors increase the rate of a chemical reaction between a solid and an aqueous solution? So these are literally the only factors, and decreasing the volume are the only factors that will increase the rate. So addition of a catalyst, yes, of course, catalysts are made to increase the rate. So when you add a catalyst, it's not going to be used up, but you're going to get a higher rate. Increasing the concentration of aqueous reactants. Now look, for this one, be careful. It has to either say aqueous or gaseous reactants. You cannot, if it says solid or liquid, it's immediately wrong. Like, it has to be gas or aqueous. You can't have anything else. Increasing the surface area of solid reactants. For solids, you can increase the surface area. Like, you could cut it, you could grind it, make it into particle, like into dust or powder. But you can't, like I said, a solid always has a constant concentration, so it can't, you have to increase surface area for it. Increasing the temperature in all cases and adding a catalyst in all cases are going to increase the temperature. There's no nothing like that needs to happen for, like, it doesn't have to be solid, liquid, or gas for it to increase the rate when you add a catalyst or increase the temperature. It's only surface areas, only for solids, and concentrations only for aqueous and liquid. And yeah, so next question. And increasing the volume, by the way, increasing the volume is wrong because if you increase the volume, it's like you're giving them more space to bump around. Like, if your particle is here, it's gonna take more time to bump into this wall than if it were in a container this big and like here. But would it not have a rate? No, it would have a rate. It's just it won't increase the rate. It's gonna make it slower. That's why it's wrong. If it said decreasing the volume, which means increasing the pressure, yeah, it would be right. But no, it didn't, so yeah, it's not right. Next one. Okay, so when will this equation reach equilibrium? When all the NO2 would have changed to NO. This would be right if this wasn't an incomplete reaction. This is agreed to reach equilibrium. So technically, you'll never have it all changed to NO, because when it's changed to NO and CO2, it's gonna go back to being this. They're just gonna keep on reacting, giving and taking, becoming products, becoming reactants. They're just gonna keep alternating between the two. So you can't ever really have all of it changed. When the forward reaction rate is faster than the reverse reaction rate. The word equilibrium, you could tell, it's part of it says equilibrium. So your rates have to be equal for it. So when you have your forward reaction rate faster, it's not equal to the reverse reaction rate. That's why you can't have it. When changes can no longer be observed. So when you cannot see any more macroscopic changes, let's say these are colored, they're not, but let's say once you see the color stop changing and it becomes on a set color, like a set shade, a set concentration, a set everything, when you reach that point, you have reached equilibrium, when no changes can happen, when the concentrations are constant, when color, pressure, and measurable quantities are all constant, no changes can be observed, then you have reached equilibrium. So this one is right. Now, when the forward reaction rate is slower than the reverse reaction rate, this is wrong for the same reason as this. Equilibrium, which means equal. So you cannot have anything slower or faster than the other. Like here, when the forward reaction rate is equal to the reverse reaction rate. Once you see that word equal, you're at equilibrium. Like the word gives the answer away. Now, next question. So, which of the following are true about macroscopic properties? So, they can be seen without any visual assistance. Yeah, so their properties like here, see, they're measured or seen properties like pressure, color, or concentration. Now you're gonna say, I can't see the concentration. Well, you kind of can, because like I said again, if you have a red colored solution here, and you see its color is this shade of red, and then the next minute you'll see it changing like to a more, okay, I don't have a pink color, let's say if it's changing between blue and red. Once you reach purple, which is the equilibrium, which is the middle color, and it stops changing, you could see the concentration. It depends on how dark or light the shade of the color is. That's the concentration. That's how you can see concentration. So can these be seen without visual assistance? Yeah, you don't need a microscope to see them. They're macroscopic. Macro means big. You don't need a microscope, so you can see them with your own bare eyes. So they can be seen with a microscope? No. They're macroscopic. Why would you use a microscope? They cannot be seen or measured? No, they could. That's why they're properties. They are measured or seen properties like pressure, color, or concentration. Yes. This is like you could see, like you can measure the pressure, you could see the color, and you can kind of see and you can measure the concentration. They are fixed properties which do not change. This is definitely wrong because concentration can change, pressure can definitely change, and color can also change. So, yeah. Which of the following can be concluded from this equation? N2O4 is at equilibrium with 2NO2. Okay, so let's see our options. The reaction is fast. How do you know? It never told you anything about being fast or slow. You can't tell if it's fast by looking at a reaction, so obviously wrong. NO2O4 molecules and NO2 molecules are always present in the reaction mixture. Like I said before, once it's at equilibrium, they keep on alternating. So the minute this turns into product, this will go back to turning into, this will become the product. So in this case, both NO2 and N2O4 are products and reactants at the same time. Because when this is reacting, this is the product. When this is reacting, this is the product. So are they always going to be present? Yes, they're not going to go anywhere. They're not running away. They're going to stay if you have them in the same container. This can't leave and this can't leave. They're both gases and they're both going to keep alternating and turning into each other. So they're always present in the mixture. 2 molecules of NO2 are consumed for every molecule of N2O4 formed. So let's see. You have the reaction says that you need 2 NO2 molecules to make 1 N2O4 molecule. So you're going to say, but this is the reactant side. Like we said, they're both reactants and they're both products. So 2 are consumed for every one N2O4 molecule made, and 1 N2O4 is consumed for every 2 NO2 molecules formed. They can work both ways. There will always be twice as much NO2 as N2O4 as at equilibrium. You're gonna say, yeah, because it's NO2, 2 NO2. This isn't right, because you need, like, look, this now is balanced. Like if you multiply the 2 by everything in here, you're gonna end up with also 2 with N2O4. They're the same thing. So you can't say you have twice as much. It's you have the exact same amount. Like they're balanced. Don't have twice as much at equilibrium. And the forward and reverse reaction may take place simultaneously. Yeah, they do take place simultaneously because, like I said, they turn into reactants and products at the same time. While this is turning into reactants, this is turning it back into products. Same thing. So, yeah. Okay, next question. Which of the following are correct about equilibrium? So, about equilibrium, now this lesson is like memorize these points. So, chemical reaction process proceeds oh my gosh, I can't talk. Spontaneously to approach the equilibrium state. Yes, they have to happen at the same time if they're equilibrium. Like I said in the previous example. Tend to favor the state of lowest randomness. No, this is wrong. It's greatest randomness. That's why this option is right. Like memorize it. Once equilibrium always favors the greatest randomness. So yeah. At equilibrium state is the equilibrium state is a compromise between minimum energy and maximum randomness. Because if you're gonna like see at equilibrium at very low temperatures, equilibrium favors molecular substances with the lowest heat content. So it's minimum energy. So if you say greatest randomness and minimum energy, the equilibrium is practically just the compromise. It's the state in between. If you cannot choose between two things, you're in between it. That's equilibrium. Same thing. So it's either you have a tendency towards minimum energy or a tendency towards maximum randomness. And by the way, randomness increases from solid, liquid to gas. So the more you approach the gas state, the more random it is. Like, I'm gonna draw it to explain. This is the way for randomness, increasing randomness, higher randomness. I'm just gonna write random because like I think you can get it if I write random. So yeah, this is the way for randomness. At high temperatures, randomness is more important to the equilibrium than energy is. At low temperatures, it favors lowest heat content, which means lowest energy. And another thing about this point is in at low temperatures, in exothermic reactions, like this isn't really to do with the question here, but they could bring something about it in the exam. This is an exothermic reaction. We know that because it's sloping down. Here's your reactants, and here's your products. At low temperatures, in exothermic reactions, the products are favored. The thing at the lowest heat content, like the lowest point, lowest potential energy, you could say, it's favored. So in exothermic, its products are favored at low temperatures. And let me draw the endothermic. And endothermic, this is your reactants, and these are your products. Excuse my R, it's terrible. Okay, yeah, so R here is lower than product, so this is exo, and that is endo. So at endothermic, the reactants are favored, and in exothermic, the products are favored because you look at the lowest thing. But this is only at very low temperatures. At high temperatures, always look for randomness, which is this. At low temperatures, first, like you need to see lowest heat content and if it's exo and endo. They most likely won't ask you tomorrow about the exo and endo thing, but it's good to know it in case they do. So, yeah. And this, like I said, compromise. It's between this and this. That's what equilibrium is in case of normal temperature. Like if there's medium temperature, not too high, not too low, it's going to compromise between the two of them. So, okay, so when is equilibrium reached in this case? When we can detect no more evidence of change. So when change stops, that's when you reach equilibrium, when it's just constant. Constant or equals equilibrium. Constant. By the way, equilibrium is expressed by this double arrow thing. So anytime you see me writing this means equilibrium. So when equilibrium is reached, there's no more evidence of change. Everything is constant. When we can detect an evidence of change? No, we just said no more evidence of change. When the pressure measured remains constant. Once you see constant, you know you're at equilibrium. When macroscopic properties become constant, not microscopic, when macroscopic properties become constant, then these two are definitely right, because pressure is a macroscopic property. When the chemical system pressure rises, if it rises, it's not constant, so it's definitely wrong. So macroscopic properties, we already said this, it's color, concentration, pressure. Mass number, no, because that's microscopic, you can't see it by looking. And atomic number also, you can't see the protons and the electrons by looking at it. So Le Chatelier states that it's called LCP. I'm not gonna try because I'm gonna butcher the name. So just memorize it because this is a law. Like it's not a law, sorry, a principle. So this one, memorize it. When an equilibrium is subjected to a change, it will partially counteract the imposed change. You'll see what partially means, like in the coming activities, because it won't change the whole system. It's gonna change parts. Okay, so which of the following indicates saturated vapor equilibrium? If you see arrows like this, it's not equilibrium. They have to be like equal to each other in size to be equilibrium. Like, see, this, it's not a lot is coming. The rates aren't equal of going and coming. Like you're gonna say, yeah, they are going in both ways, yeah. But we know for equilibrium, rates should be equal. So this and this should be the same length, not different lengths. Based on the collision theory, a decrease in the temperature of the reaction decreases the rate of a reaction because the number of effective collisions between the particles decrease. We said decrease temperature, you're decreasing rate, you're decreasing the particle effective collisions. Anytime you see a decrease in temperature, don't even think twice. It's immediately decrease for everything. Okay, so the potential energy of the reactants is how far it is from this line, the x-axis. For reactants, you have this as your reactants, because this is the starting point, so it's A. For products, this, ending point, C. Activated complex is your highest point, which is B. Forward reaction is Y, and backward reaction would be something like from here to here, I think, if I remember. Yeah, it's like from here to here, that's backward, but they didn't ask for it. And enthalpy change, which is just the difference between the heats, is here. These two, which is X. Okay, so... Oh, I skipped a question. Lower temperature. Okay, so here they told you that excess calcium carbonate. Calcium carbonate is your excess. So hydrochloric acid is your limiting. Always, we're gonna look at the limiting. If anything in the limiting changes, your end changes. So if anything decreases in the limiting reagent, your endpoint will be lower than the rest. If anything increases, it's gonna be higher. So let's read. Lower temperature, it's gonna decrease the rate, but it's not gonna make it any lower. Lower concentration of our limiting reagent, gonna change the entire ending completely. Lumps instead of powdered. Powdered, which is smaller and finer, has more surface area than lumps. So you're decreasing the rate. And catalysts increase the rate, but same ending. So yeah. Next question. Okay, based on the collision theory, a decrease in the concentration of the reactants decreases the rate of reactions, and the number of collisions between particles decreases. Decrease in concentration, decrease in rate, and decrease in collisions. This is by the collision theory. Okay, so here we have something about the equilibrium again. Okay, before the equilibrium states, one of reversible chemical reaction. So you're before equilibrium. The rate of the forward reaction is gonna decrease, and the rate of the reverse reaction is gonna increase. What they mean by this is they're both gonna try to find their middle point, the point where they're both comfortable at. So here, forward is gonna start up high, reverse is gonna start up low. This is gonna what happened? This is gonna get higher to reach, and this is gonna get lower, both of them to reach a midpoint. You always need a midpoint. And since I started with this part, let's continue with it. It's gonna reach the midpoint and gonna continue constant. Like we said, equilibrium means constant. This, they don't touch, they don't reach their midpoint. Here, how did they just stop? This is literally impossible, like they can't stop. And this is, yeah, how are they gonna go back? They remain constant. So before equilibrium, forward decreases and the reverse increases so they can reach the midpoint. At equilibrium, the rate of the forward and the rate of the reverse are equal. Rates are equal. See, they're equal. But the concentrations are constant. Concentration always constant. So chemical equilibrium is referred to the dynamic duo due to the existence of two opposing microscopic processes that continue to take place simultaneously at the same rate with no macroscopic changes. What they mean by microscopic is your forward and reverse rate. That's microscopic. And the same rate, you know they're happening at the same rate when they reach equilibrium. And macroscopic changes are the changes you can see and that we know do not change after equilibrium. Okay, so now we're going to talk about the LCP part. We know in concentration in LCP, when concentration differs, let's read, when Cl2 is removed. Cl2 is removed means that the concentration of the reactants decreased. So, like we said, it's trying to partially counteract. So if this decreases, it's gonna try to find a way to increase it again, because it's at equilibrium. Anytime anything you change it makes the equation different, it's gonna try to make it back to normal somehow. So when you're removing Cl2, equilibrium position shifts backwards, because this is where this is backwards, this is forwards. So backward is where you made the change. So it's gonna shift backwards to add concentration to this side. You're gonna try to get the concentration of this side up to be equal to like this. So if you're going backwards, this is gonna decrease. And the concentration of CO2, Cl2 decreases because you're going this direction. But when you add SO2, now you have, when you add SO2, now you have too much, like you added concentration to the reactants. So like your plus concentration. But so now you need to increase the concentration here to make it like able with this. So you shift the entire thing forwards, and the concentration of this will have to increase if you add anything on the reactant side. Okay, so now let's read. Using LCP to predict the shift of the equilibrium position if the pressure is increased by decreasing volume. Okay, so now look, be careful. Like I said before, never look at solids. Never look at solids because it's the gaseous moles. Here in this reaction, we know that when pressure is increased, you need to look for the lowest number of gaseous moles. G moles. Least gaseous moles. You can't have solids. So we won't count this all together. Let's count how many moles. You have 1 mole here, 1 mole here. If they're equal moles, like you have 1 mole here and 1 mole here, no change. We don't count C because it's solid. Now let's go here. You have 2 moles on this side. First you have to check, are they all gases? Yes. You have 2 moles on this side and you have 2 and 1 mole here. So you have 3 moles on this side, 2 moles on this side. We said lowest gaseous moles. So it's gonna go towards it. And the lowest here, if here is 3 and here is 2, 3 is bigger than 2, so it's going in this direction. Now it shifts backwards. Here, let's do it again. Gas, gas, gas. Now let's see. Here you have 3 moles. And here you have 2. So Yeah, this is bigger. So it's gonna move in this direction. That's what I like doing. See which one's bigger, like draw the sign for which one's bigger and just draw an arrow. It's most likely gonna show you which direction it goes to. Like see, shifts forward, shifts backward. Now here you have 2 moles on this side, and you have 1 and 2 moles on this side. If they are equal, there is no change. And yeah, let's go to the next question. How many questions are left? Wait. Okay, a lot, so I'm just gonna go back to this question. Okay, so LCP always favors the endothermic direction. Always, just have it as a rule. It's gonna favor endothermic in the endo direction. So endo direction. So let's see which one's this equation. This equation is endo because we can see that this is in the reactant side. So endothermic direction is this direction, which is backwards. So it shifts backwards. Now let's see. SO3 is where? SO3 is here. So it's shifting in the direction of SO3. If it's shifting in the direction of SO3, then it increases. Because whenever it's shifting to the side, if SO3 is on the side where it's shifting to, it's gonna increase. But let's say SO3 was here. This wasn't SO2. Let's say this was SO3 and this was SO2. Then it's gonna decrease because it's going in the opposite direction. It's shifting in the opposite direction. So now here they told you it's exothermic because there's negative. So here would be your negative 2.7. Well, sorry, like when you put it inside, your equation is going to be positive 0.6. But either way, it's in this side. If this is your exothermic side, then when going back, this is going to be your endothermic side. So again, it's going to shift backwards. It's opposite of exothermic, so it's going to the endothermic. Because like I said, when you reverse this equation, the plus 27.6 is going to make, so it's going to be endothermic. So it shifts backwards, and now CO2. CO2 is here. It's shifting in the opposite direction of CO2, so CO2 decreases. If it were shifting in the way of the CO2, it's going to increase. But it's not. It's shifting backwards, so it's going to decrease. Okay, so catalysts now. You're adding a catalyst on the chemical reaction using LCP. The equilibrium position is attained faster and the concentration of CO2 remains constant. When you see catalyst, no, it's not going to favor anybody. It's not going to shift anywhere. It's going to remain constant. No change is going to happen. Just a catalyst will increase your rate, will like be faster, best. That's the only thing. Okay, so for an inert gas, when you're adding an inert gas, which means a noble gas, a gas that doesn't react with equations. So this is gonna not do anything practically because it's not reacting with anything, it's not changing anything. So equilibrium position is not affected at all. Like it doesn't even care, it won't even care, it won't consider it there. And the concentrations are gonna remain constant. Just take it as a rule. And when we say the gas above the liquid is saturated, we mean that the rate of evaporation is equal to the rate of condensation at a certain temperature. This is like the little beakers we saw in the previous questions when I told you they have to be at equilibrium and they have to be equal to each other. Like just take this phrase and know it's equal to. Okay, so let's say you removed which of the following species increases in concentration when B decreases. Like I said, you removed B, now it's gonna have to increase A so it can be equal to these, like it can compete with these. Like if you have, let's say it as if you have teams of 2 teams competing in something. If one team has 2 players and the other team has 1 player, you're gonna have to give it an advantage. You're gonna have to increase something for it. You're gonna have to give it a bonus thing so it can actually compete and it will be fair. It's the same idea. If you remove B, there's one teammate lost. You're gonna have to give A an advantage, so it's increasing its concentration so that it could compete with C and D. And they're not competing. I'm just using an example, like to make the idea clear. Okay, decreasing volume, which means increasing pressure. So yeah, see, pressure is increased. Let's see, NO2O4. We first, like I said again, least gaseous moles. These are both gas. If it's a solid, by the way, just count, if, like, let's say here's a solid, this has 0 gaseous moles, no matter what the coefficient is. So here you have 2, here you have 1. So this is the side where it's going to favor. So N2O4, which is on the side it's favoring, is going to increase. But 2NO2, which is on the side it's not going to favor, is decreasing. And now last question. If the pressure of the systems increase, the system will counteract by shifting. Okay, so again, pressure is decreased, so pressure is increased, so we have to look for least gaseous moles. Gas, gas, gas. Here you have 2, here you have 3. So this one's bigger, so it's gonna favor this one. It's gonna go in this direction. So it's gonna shift. What's this direction? It's left. And the amounts of O2 and H2O, which are these ones, which are not on the side where it's shifting to, will decrease, and the one where it's on the side of it's shifting to, which is H2O, will increase. Just like be careful when they say increase and decrease, and inshallah you'll most probably get very high marks in your exam tomorrow. And yeah, it's really easy. It doesn't have any calculations, so it shouldn't be too hard. Yalla, bye.